All right, students. All right, let's work through exam number 2 here. And we'll go through and hopefully you can check your answers, give you some idea of your score. Remember, these are multiple choice and they're 2 points each. And there's 4 from each chapter. So going to our work and energy chapter, chapter 7, that's what these first 4 are about. It says, how much work is performed by the gravitational force F on a synchronous satellite during 1 day in orbit? So remember, we have this definition, and it's kind of a strict definition. It's force times distance, but for this problem, it's going to be real important you remember that the distance is in the direction of the force. And so if you had like the planet Earth here and a satellite going around, the force of gravity is pulling in towards the Earth, and it is moving perpendicular. So there is no distance in the direction of the force. So it would be F times 0 distance, which would be 0 work. And so I think that makes B the best answer, 0, because the force is perpendicular to the velocity. So there's the first one. And again, that's that strict definition of work, which, if you recall from the lecture, I said, yeah, it's really, really strict, but it's in a good way, because without that strictness, we wouldn't really have the principle of conservation of energy. And so it's that understanding of how nature works got to be in the direction of the force that's important here. And that couples in with Newton's first law, but I better move on here. All right, so a 1,200 kilogram frictionless roller coaster starts at a height, and so it starts from rest, that's important, at a height of 20 meters. So it's 20 meters up, starts from rest. What is the kinetic energy when it goes over a hill that has a height of 10? So this is that conservation of energy. I was trying to say you would have a kind of a before and an after. So you would have this mgh before, which would be 20. And you might even say plus 0 for the kinetic energy, but because it's at rest. And so this is the total energy that the roller coaster has. And it's going to keep that same amount. And so as it goes down, it could go down to a hill that has a height of 10, or it could go below it and come back up. It doesn't really matter how it got there. It just is now at a height of 10. So there would be kinetic energy plus its potential energy, which would be mg10. So the kinetic energy would be some number such that when you added those two together, you got this number, and there's our R0. So if you move this to the other side, you would have an mg10 is equal to the kinetic energy, and taking the mass as 1,200 and g roughly as a 10 and times a height of 10, we're looking at 120,000. And so it looks like C would be the answer to number 2. And that's that principle of conservation of energy. So number 3 says a block of wood loses 160 joules of gravitational potential energy as it slides down a ramp. Okay, so it's going to start up here. It's got a lot of energy, mgh. Doesn't really say, let me keep reading, if there's any kinetic energy to begin with, but a block of wood loses 160 joules of gravitational potential energy as it slides down the ramp. So as it slides down that ramp, that 160 needs to go somewhere. It lost it. And the principle of conservation of energy says it goes somewhere. So if it has 60 joules of kinetic energy at the bottom of the ramp, I think this could have been written better to say that it had 0 at the top here. But let me keep reading. If it has 90 joules of kinetic energy at the bottom of the ramp, we conclude that, and so if it only has 90, there must have been 70 lost somewhere. So 70 joules of energy was transformed into another form. And I'm going with that one. They already said we lost it, so it can't be that one. We have a force, can't be that one. Yeah, so it's got to be D. And we can't lose that much energy. Didn't have that much to lose. But we definitely know it was transformed into another form. Yeah, even if it had some kinetic energy. So I guess it was okay not to say anything about the kinetic energy at the beginning. So the way they phrased it. We know the 70 went somewhere else. That's our conservation of energy. All right, looks like the last one on energy. It says, if a 60-kilogram sprinter can accelerate from a standing start, so 0 speed, to a speed of 10 meters per second in 2 seconds, what average power is generated? So power is the energy per time, and so we know the runner is going to gain some kinetic energy. That's 1/2 mv squared, and it looks like it does this in 2 seconds. So if we take a 1/2 and multiply by the mass of 60 and multiply it by the speed of 10 and square it and divide it by 2, let's see what we get here. This would be 100 when we square it. Maybe I'll take half of that for a 50, because a 50 times a 60 makes 3,000. Cut that in half, and we're at 1,500. So 1,500, and these would be in joules and seconds, which is measured in watts. So all the units would be watts, and that's fine. All right, so there's a question on the rate of energy, power. All right, so now we get to question 5, and I'm sure this now goes into our rotational chapter, our chapter 8. It says, if a ball with a weight of 30 Newton hangs from the end of a 1.5 meter horizontal pole, so we've got this pole, and we've got it horizontal, and this is being some ball at the end pulling down with 30 newtons. It says, what torque does the ball exert? So we learned that torque is the distance multiplied by the force. So the distance being 1.5 meters, and the force due to the weight is 30. So 30 times 1.5 is 45, and the units would be Newton meters, and so it looks like C would be the right answer there. An object's resistance to change its rotational velocity, okay, is called its rotational inertia. And so remember, inertia is its resistance to change its translational motion. So mass and inertia, or mass is the measure of its inertia. And so this is a translational stuff. Torque is what makes something rotate, but this is the resistance to rotate. All right, so 6 should be D. The reason a figure skater spins slower as he extends his arms outward. So remember, this is the conservation of angular momentum. So we have kind of this before and after. And so the angular momentum L would be this rotational inertia times rotational speed. And so somebody who is spinning can take advantage of this. Skaters and gymnasts and divers, motorcycle stunt riders, all these take advantage of the principle of conservation of angular momentum, because what ends up happening is they say, okay, well, I have this much now that I started, and if they were to change their rotational inertia, which has to do with where the mass is distributed, then that would change their angular speed. So in this case, the figure skater is going to extend the arms out. So this number would get bigger, making this number smaller, so that we can conserve angular momentum. So I suppose if one of the options here was because of conservation of angular momentum, I would go with that. That's not here. But the part of this is where the rotational inertia is greater, and then the speed would get smaller because of conservation of angular momentum. So that would be a good way to answer it, D. Another one on rotation. It says when a gymnast performs a double somersault with a full twist in the middle, the angular momentum of the twist comes from the let's see, what are they trying to say here? Comes from the torque. No, there's no torque due to gravity, and it doesn't come from a force. Force doesn't even make things rotate. Force makes them translate. So A and C are terrible choices, but they do want, as we talked about in 7, this is conservation of angular momentum. It comes from the somersault motion. We don't gain any angular momentum. We can move it to the twist or something, but it comes from the somersaults motion. So B would be the best answer there by far. Okay. So on to number 9 here. And number 9, I think, is still... No. Okay, now we're changing gears here. So that number 8, that was the end of chapter 8 and our rotation. Now we're going to go into chapter 11. 1, 2, 3, 4. So these 4 from chapter 11, and they're on the structure of matter. And so we have 1 liter of oxygen, and it has a mass. So they tell us of 1.4 grams. You don't need to figure that out, which I don't think we really covered, so I don't think you can. So we'll just know that we have 1 liter and we have this much mass. And the oxygen molecule has a mass of 32 AMUs. How many oxygen molecules are there in this 1 liter? Now, keep in mind that when we give the atomic mass of something, in this case 32, there's 3 meanings to that number. The first one we talked about is it's the number of nucleons. That won't really help us here. The other thing we talked about is this would be the mass in atomic mass units of 1 molecule of oxygen. All right, so 32 atomic mass units is the mass of 1 oxygen molecule. And I'll just say number of nucleons. But this is the last one, is the one that's really relevant for this problem, is this would tell us that 32 grams is the mass of 1 mole. Now, we don't have 32 grams. If I were to tell you I had 32 grams of oxygen, you would be able to tell me you had 1 mole. I have a fraction of that. So I would say that I have 1.4 over 32 of a mole. I have something less than a mole. Remember, it takes 32 grams for a whole mole. So this is the number of moles that I have. And I know that a mole, Avogadro's number, this is how many molecules are in a mole. And so that's the key to the problem. To start off by saying, what is the meaning of the AMU, which then would tell you what fraction of a mole you have. So I have about 4.4% of a mole. And knowing that this is, Avogadro's number, this is how many are in a mole, I would have 2.6 times 10 to the 22. And it looks like that B is the closest one there. Nice. What Fahrenheit temperature corresponds closely to? So if you remember our temperature scales from this chapter, if you take it in Celsius, you multiply it by 180 over 100, which is 9/5. In fact, maybe I'll write it as I like it better so I can remember where it came from. 180 over 100. That is how many divisions there would be on a Fahrenheit scale. A Fahrenheit scale would be offset by 32, so I add 32, and that would be my temperature on the Fahrenheit scale. Now, you guys have an open test book, so hopefully you just looked in the book or the lecture notes and you saw this. So let me take 180 and divide it by 100, and then multiply it by 45, and then add 32, and we're looking at 113 degrees Fahrenheit. Nice. All right, 11. Which of the following doubles with the doubling of the absolute temperature of an ideal gas? Now this is a good one, because through this chapter we were talking about higher temperatures correspond to more motion. And it's true it's more motion, but later on in the chapter we got more specific. We said not only is it more motion, what kind of motion? Because is it a doubling of the speed? Is it a doubling of the momentum? Is it a doubling of the kinetic energy? I mean, yes, temperature is related to motion, but all of those are related to motion. And they're related in a different way. So which is it? And we said temperature, and if I can use a fancy math term, is proportional or related to the kinetic energy. All right, so when it says which of the following doubles with the doubling of the absolute temperature, it would be the kinetic energy. So temperature is correlated with motion. Yeah, what motion? Momentum, no. Speed, no. Velocity, no. It is the kinetic energy. And so 11 should be D. And in fact, if you thought of it as related to the speed, you would probably run into troubles here because, well, I guess if it's just speed, momentum and velocity actually have direction, so you could justify speed over the other ones. But anyways, these are all linear with speed. This is the only one that is quadratic, so this is kind of the oddball, and I would have a hard time picking this one over this one over this one if it was proportional to speed. But it's proportional to kinetic energy, which is proportional to the square of the speed. So that means if you increase the speed by the square root of 2, because you're squaring it, you would get 2 times the speed squared. So you don't have to double the speed to double the kinetic energy. In fact, if you doubled the speed, you would quadruple the kinetic energy because it's speed squared. So you would increase the speed by the square root of 2, which is 41%. So if you increase the speed by 41%, its kinetic energy would be doubling and its temperature would double. All right, looks like we got last one here from chapter 11, number 12. If you hold the temperature of an ideal gas constant, what happens to its volume if you double the pressure? Now, I was trying to show you this connection here, that the pressure times the volume equals the number of moles times this constant times the temperature. Now, for this case, it says you hold the temperature a constant, so that's a constant. And it kind of indirectly applies that you don't change the number of molecules because it says if you hold a gas, and so it's the same gas. And so the point is the initial pressure times the initial volume would equal to whatever these come out to be. I'll just call them a constant because they're not going to change. And that has to equal to the final pressure and the final volume. And so this is referred to as Boyle's law, since he was the first to discover it. But you would have some initial here, and it says here, what would happen if you doubled the pressure? So this pressure goes up by a factor of 2, which if they got to multiply out to be the same number, this constant, then this must go down by a factor of 2, meaning 1/2. So is cut in half would be the best answer there for 12. Okay, and then on to, I guess this would be chapter 12. And 1, 2, 3, 4. The next 4 are coming out of chapter 12, which is those Archimedes Principle and Bernoulli's. I think these are Archimedes. Oh, there's a Bernoulli there. But let me go right here. It says salt water is slightly denser than fresh water. Hopefully you remember that from class. It says, will a 12-pound bowling ball feel a greater buoyant force sitting on the bottom of a freshwater lake or the bottom of the ocean? All right. So the thing to remember here, it is completely submerged. So I'll draw two pictures of this bowling ball. Both of them are completely submerged. And Archimedes' principle says the buoyant force is, and that's the question. The question is, which has a greater buoyant force? Okay, so the buoyant force is equal to the weight of the displaced fluid. So since the bowling ball under freshwater or salt water is completely submerged, it would have the same displacement of volume. But that same volume of salt water, being more dense, would actually weigh a little bit more. So the weight of the displaced fluid would be greater for the salt water. So it would be a greater buoyant force as it sits at the bottom of the ocean. And I'll say it again. Be careful here. They would displace the same volume. But that same volume of salt water weighs more than that same volume of fresh water. So that's why it comes out to be more for the ocean. And please don't confuse this with the one we did on a homework. I remember making a video solution for this where there was a ship that was floating. See, in that case, the ship could move up or down as it floated and didn't always displace the same volume. But this one, since it sinks to the bottom, it's displacing the same volume, which makes it a different weight. But for the floating ship, it turned out to be the same weight, but it's not the same volume. And so there's a very important difference here between an object that's floating and an object that's sinking. So hopefully you didn't confuse that one here in 13. All right, well, let's keep going here. Three spheres have the same volumes, and they all float in water. Sphere A, B, and C have the mass of 25, 30, and 35 respectively. Which sphere floats the highest? All right, so if I were to draw a picture, and let me not draw all three, I'll just draw one of them, and then talk about it 3 different times. But since it is floating, what's pulling it down is its weight, mg, and what's lifting it up is the buoyant force, which the buoyant force is equal to the weight of the displaced water. So anything that's floating here, we know, since it's not accelerating, the sum of the forces have to be 0, which means that the buoyant force going up and gravity going down have to be equal. So the buoyant force has to equal the weight of the object. So for this case, the heaviest object, it looks like C. Spheres A, B, and C have a mass of respectively. Okay, so sphere C is the heaviest. It would need the most buoyant force. And remember, you get the buoyant force. The buoyant force is equal to the weight of the displaced fluid. So that heavier one is going to have to displace the most water, which means it would be sinking the lowest. Now, that's not the question. The question said, which sphere floats the highest? All right, so the highest one means the one that would have to displace the least amount of water. And displacing the water would have to do with its weight. And so the lightest one would displace only 25 grams of water. And so it would be floating up the highest, whereas B would need to go a little deeper so it can displace 30 grams of water. And then C, deeper still, they would have to displace 35 grams of water. So the one that was going to displace the least and therefore float the highest would be A. All right. Here, a plastic bobber, it just barely floats in water. Now, barely floats in water, this is the water line, means maybe it is barely above it. Okay. But what that would also mean is that it took really the whole volume of the object to eventually equal the whole weight of the object. Because remember, the one we just talked about, if it's going to float, and I'd call this still floating and sink down to the bottom, the buoyant force has to equal the weight. So to get enough buoyant force to equal the weight, we essentially had to displace the whole object here, okay? And this is, of course, what it would tell me. It says if it weighs 2 newtons in the air, what is its volume, okay? So the fact that it weighs 2 newtons comes back to here, which means that the buoyant force is 2 newtons. Okay? And that 2 newtons then would correspond to, and they'll go mg, now maybe divide by 10 here, is a mass here of 0.2 kilograms. Since I'm going to treat g as a 10 and meters per second squared, and then this newton, of course, is a kilogram meter per second squared. Maybe I'll write this as 200 grams. So that's the key to the problem. Again, Archimedes Principle. I know that the buoyant force is 2 newtons because it weighs 2 newtons. Okay? And then buoyant force is equal to a weight, so I'll divide by g to get its mass. So I know that this thing has a mass of 200 grams, but it's also displacing 200 grams. Okay? And here's where the density of water comes into play. This is the phrase where it just barely floats, because to displace 200 grams of water means, and taking the density of water, means you've got to displace 200 cubic centimeters of water. And it says the thing is essentially completely underwater. And so that's the logic in 15. That you've got to figure out what the mass of the object is based on its weight. That would displace the same amount of water, which then corresponds to a volume, since the density is for every 1 gram, you get 1 cubic centimeter. So if I've got to displace 200 grams of water, I've got to displace 200 cubic centimeters for the volume. All right, well, one more here from, I believe, this chapter, and I think this is a Bernoulli one. It says an incompressible fluid is being pumped through a pipe that has a narrow region. All right, so pipe is wide and maybe narrows down. Now, if water is flowing through that, the thing to recognize here is it's going to have to go really fast. This would be if you've ever used a garden hose and you put a nozzle on it. That's what it is. In order to get the same volume through here, it goes really fast in the narrow part and slow in the broad part. Okay. Now, Bernoulli's principle says that the pressure drops. So this should be low pressure when something is going really fast. And over here then should be the high pressure. So it says the pressure in the narrow region is, and then I guess this would be lower than the wider regions. So A would be less than, the same, greater than. So 16 should be A. Okay. Well, finally, to our last chapter for this exam, chapter 13, where it's on our heat and our specific heat and latent heats. It says, how many calories are equivalent to 21 joules? Well, 4.186 joules is our conversion of 1 calorie. So, if I had something like, I'll just do a unit substitution. I guess this is back to chapter 1. So if I have 21 joules, 21, I can replace a joule right here. So if you think about this equation as dividing both sides by 4.186, on this side I would get just a joule. So I'm going to replace a joule with 1 calorie divided by 4.186, which is going to leave me with calories, which is the question, how many calories? And so I would have something that would look like 21 divided by 4.186, and it looks like we're around 5. So 17 would be A. Why do climates near the coast, like Santa Barbara, tend to be more moderate? And moderate means it doesn't get hot in the summer and doesn't get cold in the winter. Are more moderate than in the middle of the continent. And you can imagine, since the water has something to do with it. But here it says, and we kind of went over this, we had this exact same question on the lab, because the water has a relatively high specific heat. That is an excellent answer. Let's read the other ones. Because water has a high latent heat. Although that's true, it's really more about not evaporating the water, but warming of the ocean. Because the coasts have lower elevations, no. Because it rains a lot on the coast, no. All right, so it's A, and on our, you see it right now, our ocean, even on these starting to get warm summer days, just doesn't warm up. I wonder what our ocean temperature was. I was just out this weekend, and I thought it felt pretty warm. But my buddy, I said, hey, it's pretty warm out here. And he said, no, you're just fat and out of shape and you're tired and working hard, so it feels warm, but it's really not. So I don't know. It felt like the 60s to me, but he said it was still 59. But anyways, the point is our water is relatively cool, and even with the sunshine, it still doesn't get that warm. And that's because of that high specific heat. And the advantage for a coastal city then is that now the ocean, because of the large specific heat, really doesn't warm up. And so the ocean stays 59, 60, 61 degrees. And then as the air blows across the surface of the ocean, it gets cooled, and then that comes in to Santa Barbara. And so Santa Barbara, it's really hard to get us above 65, 70 degrees because the coolness from the ocean keeps us cooler. And I think today, we're gonna maybe hit 70, but it's kind of challenging to hit 70, and warmer than that. Now, when the wind blows the other direction, now that's a different story, because now the ocean can stay cool, but we don't get that transfer of heat blowing over the ocean. So those Santa Anas is when we can really get hot in Santa Barbara, and those aren't common, fortunately, but they are hot when it does happen. All right. 19. It takes 250 calories to raise the temperature of a metal ring from the 20 degrees Celsius to 30 degrees Celsius. If the ring has a mass of 90 calories, what is the specific heat? So the definition of the specific heat is the amount of energy, so in this case 250 calories, needed to raise 1 gram. So we would need to divide that by 90 grams. And warm it only 1 degree Celsius. So we would have to divide that by the 10 degrees that it's warming up. So 250 first divided by 90, then that divided by a 10 is about 2.8. I'm sorry, 0.28. calories per gram per each degree. Okay. And then finally, the last one from chapter 13 is a steel railroad rail is 24.4 meters long. How much does it expand during a day when the low temperature is 50 degrees Fahrenheit, that's 18 degrees Celsius, and the high is 91 degrees Fahrenheit, or 33 degrees Celsius. Still has a coefficient of expansion. And so this equation for the expansion, the alpha is that expansion coefficient. So 0.00011 is how much it expands, really how much it expands per each meter per each degree Celsius. So we would have to multiply it by the length, the 24.4 meters, and the temperature increase. And it looks like this is a 15 degree increase. So that's why we like to say this is how much it expands for every meter and for every degree increase. And so in this case, we've got 24 meters and we've got 15 degree increase. So 0.000, 4 zeros, right? 1, 2, 3, 4 times 1, 1. Then times 24.4, then times 15, and we are, oh, they gave us in millimeters. Okay, I was looking at like, uh-oh, they don't seem to match. Let me just call that 41 meters. But it looks like now we've got to move 3 decimals to make it millimeters. And so it looks like A is the answer. All right. Well, I hope those went well for you. Those were some good problems, even some hard problems in there too. Just kind of thinking what might be the hardest one. Maybe this last one I just did. I don't know. Or maybe it was 16. Well, in either case, let me grab myself a legal pad here and say, all right, let's start working these out. And maybe I'll do like last time, where I'll do the 2 on a page because they come from the same chapter. So, all right, so going all the way back to our energy chapter, number 21 says, if an object is dropped from rest at a height of 10 meters and it falls 7 meters, what is its speed? So this is the conservation of energy. I'll put before and after. I'll put kinetic energy plus potential energy must equal to kinetic energy plus potential energy. And this first part of it makes it very clear that it is dropped from rest, so the kinetic energy is 0. The potential energy, okay, is related to its height, so this would be mg10. Now, what I think can make this problem a little bit hard is they don't tell me the mass. And if I dwell too much on that, I'll feel like I'm stuck. But it looks like it's going to cancel off, so I can just put an m there and see what happens. Okay, so now we drop it, and then, of course, it would have some kinetic energy, which is this 1/2 mv squared, and its potential energy would be mg, and this could be hard, because notice it says it falls 7 meters. So that means it is at a height of 3 meters, because it fell 7 meters. And the potential energy is the height of the object, not how much it fell. Okay. Now, if I move this to the other side, I get mg times 7 equals 1/2 mv squared. And that's what I'm hunting for, the velocity. So again, this could be a hard problem for two reasons. The first one being that you might be tempted to put a 7 here, but this is its height, it's 3. It dropped down 7. So I guess you could have done this. You could have said, well, it lost this much potential energy. That has to equal to what kinetic energy it gained. And you'd put a 7 there, thinking it that way. But the other thing is you don't know the mass, but you can see that it wouldn't matter, and so that cancels off. And so now I can calculate the speed by taking g, and I'll just roughly take it as 10. You can use 9.8 if you like, times the 7, times the 2. I'll bring the 2 over, and that would be the speed squared. So if I take the square root of that, we're looking at 11.8 meters per second. All right, now number 22 is another energy one. This time they give us the mass. They say a 5-kilogram object is moving to the left with a speed of 5 meters per second. So we already are moving. Now we apply a force, a 40 Newton force, and push it to the left for a distance of 5. Well, this is like we did in the multiple choice. If you remember, that first multiple choice was really kind of hard. Maybe that was the hardest one on the test because it said how much work was done, and you want to go force times distance. But remember, it's the distance in the direction the object moves. And so we got a 0 here for number 1. Here it's a little easier because it's moving left and it's pushed to the left. So it would be 40 times the 5, which is 200. No, yeah, 200. And then it would be a Newton times a meter, which is a joule. So this would be the increase in the kinetic energy. This would be a gain of kinetic energy. So that would be the first step. I should put that here. So the work, which would be the change in kinetic energy, which would be force times distance, would then equal to final kinetic energy minus initial kinetic energy. And as we just did, the force is the 40 and the distance is a 5. The initial kinetic energy would be 1/2 times its mass times its initial speed. And so they gave its mass of 5 and its initial speed. So as I just mentioned, the 40 times the 5 is 200 joules, because this would be newtons and this would be meters. And the initial kinetic energy, I'll grab my calculator for this, because 5 squared is 25 times 5 times a half. And so it started off with 62.5. So that would mean its final kinetic energy would be 262.5, right? Don't forget that it started with 62.5 already, and what we did is we added another 200 to it to push it. So that's why its final kinetic energy would be 262.5 joules. Now, we're not quite done, because the problem says, what is the new speed of the object? But the reason I went down this road is I know that speed is connected to the kinetic energy. So this would be a 1/2, this would be a 5, and then this would be the unknown speed, has to equal the 262.5 joules. All right, so if I grab my calculator here and take this 262.5 joules, and I guess first multiply by a 2, then divide by a 5, that would be the speed squared. So if I take the square root of that, the final speed would be 10.2 meters per second. So this is what we call our work energy theorem. This is if you did some work, this is how much its kinetic energy increased by. And of course, you might forget that initial kinetic energy and just set it equal to final kinetic energy, and that would be a little wrong there. So hopefully you didn't do that. But once you know final kinetic energy, that's just related to speed. All right, so there's our page 1 of the solutions, if you will. That's the chapter 7 and the energy ones. And so let me try number 23 and 24. These should have to do with the rotation. So 23 says, if the hard drive on a computer accelerates from rest, so again rest starting at 0 speed, at a constant rate of 1,000 revolutions per second squared, how fast will it be turning after 3 seconds? Okay, so acceleration is equal to change in velocity over time. Hopefully that looks a lot like we did when we did our translational motion. That was the definition of acceleration, how the speed changes with time. Of course, in this problem, we're talking about rotational stuff. So the angular acceleration, they say, is 1,000 revolutions per second squared. The change in speed would be the final speed minus the initial speed, but they helped me out and told me right away that it started from rest, so the initial speed is 0. And all of this happens in 3 seconds. So it's really 3 moved over to here, which would be 3 times 1,000, which makes 3,000. And then 1 of the seconds would cancel off, leaving with revolutions per second. So this would be 3,000 revolutions per second, which, whoa, it's pretty fast. So I don't know if that's a realistic number, but that's what the numbers pan out to be here. 3,000 revolutions per second, because that's, most hard drives are about 7,500 revolutions per minute. So if I divide that by 60, yeah, they only get up to a speed of 125 revolutions per second. So this is, yeah, well, there are some faster hard drives. I've seen 10,000 and 12,000. I think I've seen the 12,500, and I don't think they do any better than that. And that's still only 208 revolutions per second. So that's the answer, even though I think it's a little big for realistic answers. All right, and let's try another one on rotation. Let's go to number 24 here. It says a 75 kilogram bike and the rider are traveling at 8 meters per second around a curve with a radius of 20 meters. What is the angular momentum? And so the angular momentum was the mass times the velocity times the radius. So in this case, the mass and the bike is 75 kilograms. There's the mass. They say the speed is 8 meters per second, okay? And the radius is the 20 meters. And maybe I'll do the units first, because we didn't do many units with this one, but it's a kilogram, it's a meter squared from here and here, and only 1 second. If it was a second squared, we have a fancy name for that. We call that a joule. But this doesn't have a fancy name, so I'm going to have to leave it like that. As far as the number goes, though, this is just the 75 times the 8 times the 20, and I get 12,000. And so there are the 2 answers for the rotational chapter. One with the angular acceleration and one with angular momentum. All right, well, let me call this over here page 3 as we kind of work out the solution. And same idea, let's do a number 25 and number 26 together since they're from the chapter 11. Let's see what 25 has to say. It says, roughly, how many atoms are in a box that measures, and they give the dimensions of the box. Oh, cube is a terrible word there. It should be box. It's not the cube if they don't have the same dimensions. Hint, good. Remember, roughly, all atoms are about the same size. So good. I'm glad they gave the hint there, because otherwise that could have been a hard problem. I tried to emphasize that in the video lecture, that all the atoms roughly are the same size. You know, all atoms have about 10 to the minus 10 meters in their radius, which would make roughly about, well, a 2 in their diameter. But the smallest ones, I'm sorry, I said that wrong. The diameter. The smallest ones have a diameter of about 10 to the minus 10 meters, like hydrogen and helium. They do get a little bit bigger. Some of the bigger ones can be something like 5 times 10 to the minus 10. That's a little bit on the rare side. But the point is, we said that they're all roughly the same order of magnitude, 10 to the minus 10. And so you don't really need to know what kind of material it is. And that's a big part of this problem. It doesn't say what kind of material it is. Now, I'll emphasize they don't have the same mass. So you need to know what material it is if you're dealing with the mass. That's why that multiple choice one with the 1 liter of oxygen that said it had a mass of 1.4, we needed to know what its mass was, and that it was either oxygen, or they gave the atomic mass units. They did both. They gave us oxygen and the 32 AMU. So they helped us out. We didn't have to look it up. But on something where they're dealing with how many atoms and they're giving you the mass, you got to know what material it is. But something like this, where they're talking about the number of atoms and they're talking about its size, you can get a good ballpark figure without knowing even what the material is, because they're all roughly about the same size. And that's what I'm going to do here. I'm going to say, if I could picture a rectangular box that I'll give it a height of 5 millimeters. I'll give it the longer length here of 20 millimeters, and I'll give it kind of a depth of the 10 millimeters. Okay. And maybe the thing to do is ask right here, how many atoms could you stack vertically with a height of 5 meters? And so this would be a reason why you learned division back in 4th grade. You would say, okay, take the big thing, 5 millimeters, and divide it by the little thing, the size of an atom or the diameter of an atom, and see how many fit into that. Now, we do want to be careful with our units, so we've got the denominator in meters, so let me switch the numerator into meters. So don't forget that chapter 1 stuff, but 0.005 divided by 1 times 10 to the negative 10 comes out to be 5 times 10 to the 1, 2, 3, 4, 5, 6, 7. Okay. And let's see, 10 to the 6 is a million. So this would be 50 million. So 50 million atoms stack up vertically. Now, we might do the same thing about the depth. How many atoms would fit on the depth? So we might go 10 millimeters divided by the diameter of an atom. Now, I'll save myself a little time and not actually do the work. Isn't that just twice the distance of that one? If that's 5 millimeters, that's 10. So it must be twice as big as that. So that would be times 2, which I guess you could even write as 1 times 10 to the 8th. And then likewise, how many atoms would fit along its length? And the same thing, I would go 20 millimeters. And I would divide it by the size of an atom. And again, I would change it to meters and do my division. But I'll save a little time, because isn't this one twice as big as that one? So here we got 1 times 10 to the 8th. So this would be 2 times 10 to the 8th. So this was 50 million. And I guess this makes 100 million. and this makes 200 million. So the total number of atoms would be, when you multiply them together, you would have this many, 5 times 10 to the 7th along its height. You would have 1 times 10 to the 8th in its depth. And you would have 2 times 10 to the 8th in its length. And that's how many atoms you would have here. All right, so 5 times 10 to the 7 times 1 times 10 to the 8th and 2 times 10 to the 8th makes 1 times 10 to the 24th. So that's how many atoms. And so it's just a length times width times height. Although you don't want to do length times width times height in terms of their dimensions, you want to do length times width times height based upon how many atoms are there, which we get by doing a division by the size of the atom. So there's how many atoms we have. 26. 25. Here we go. And so 26 says we have an ideal gas that is heated from 25 degrees Celsius to 175 degrees Celsius in a container with a fixed volume. If the initial pressure was 110 kilopascals, what is the final pressure? All right, so the question is about a final pressure, and we're changing the temperature, but notice they said fixed volume. And they also said a gas, so I would say the N, the number of moles, is also fixed. Because what I tried to convey in the video lectures, and I'll say it here again, the ideal gas law, PV equals to nRT, R is just a constant. And most of the time we don't even need to worry about this constant. I like to do this. I like to say, take things that are going to change and put them on one side, and things that aren't going to change, that are fixed, and put them on the other side. So I'll put pressure on the left-hand side because it's going to change, because it says this is the initial pressure and it's asking what is the final pressure. Its temperature also changes, so I'll put it on the left-hand side. But the number of moles and this constant R, whatever it is, doesn't change, and this volume doesn't change. So the way to handle these problems, and the reason I like to put everything that is a constant that doesn't change on one side is right here. It's because of this. It's because that this is a constant. So what I could do is I could say, well, if I took the initial pressure and times the initial volume, initial pressure divided by the initial temperature, that would equal this constant. Now, later on, these wouldn't change, but I would get a new final pressure and a new final temperature, but they would still have to equal that same things that don't change. And so I don't have to ever worry about the things that don't change. I can just take all the things that do change and set it equal to all the things that do change. And so now I can plug these in. So it says the initial pressure is 110 kilopascals. Okay, so I've got my 110 kilopascals right here for my initial pressure. Now, I do need to be a little careful here with initial temperature, because they did say the temperature started off at 25 degrees Celsius, but one thing that I tried to emphasize is the temperature must be on the Kelvin scale for this to work. So let's take the 273 and add the 25 and get 298 Kelvin. And that's probably an easy place to mess up, because it was given to you in Celsius. And you might want to just put it in Celsius. But that's not the case. It doesn't work. You've got to put it in Kelvin. Okay, now the final temperature, the same thing. They say the final temperature is 175 Celsius. So I'm going to add 273 to change it into Kelvin. And so the final temperature is 448 Kelvin. And the only unknown right here is final pressure. So the Kelvin will cancel off, and I will be left in units of kilopascals. And so if I take this 110 and divide it by 298, and now move the 448 to the other side, I would be multiplying. And if I hit enter here, I will get a pressure of 165, I'll just leave it there, kilopascals. So, yeah. Another thing to warn about. So a lot of little careful things here. So I hope the test's going well for you. It's real easy to kind of forget these little things here, but hopefully you practice enough problems that you said, oh yeah, I'm not going to fall for that. All right. Well, so there's page 3 and chapter 11 stuff. All right, let's go to a page 4 here, and a number 27 and a number 28. These should be from our chapter 12 and our Bernoulli's principle and our Archimedes principle. All right, so 27 says we have a block of copper that measures 4 by 4 by 4, and they get the density of copper. It's lowered carefully into a completely full beaker of water. What is the weight of the water in newtons that spills out of the beaker? All right, well, maybe I'll start with a little picture here. And fortunately, this is very much like a homework problem. But if this is the piece of copper and you put it in, the copper sinks to the bottom. And just in case you didn't know that, notice that the density is more than water. It's more than 1. And so one of the things we said about Archimedes' principle is that once you think about the buoyant force being equal to the weight of the displaced fluid, if you're putting it in a fluid, if the density of that object is more than the fluid, it will sink. And so that's why things like copper, having a density greater than 1, will sink in water. Ice, though, has a density slightly less than 1, so ice floats in water. In fact, ice is kind of fun to watch in alcohol because the density of ice is greater than that of alcohol, so it'll sink in alcohol, but it'll float in water. And so it really all kind of depends upon the density of your object and your fluid. Anyways, we need to know that it's going to sink. So copper sinks, if you didn't realize that, and I can get that by saying the density is greater than 1. So what's going to happen is the water is going to spill out, and the amount of water that spills out, so this will be my water that spills over the edge, is going to actually be the same volume as this piece of copper. Now, and that's where this 4 by 4 by 4 comes into play, because 4 times 4 is what? 16 times 4 more is 64. So this would be 64 cubic centimeters of water that is going to flow over the edge. Now, we're after the weight of the water. So how much mass is this? Well, knowing that the density of water is 1 gram per cubic centimeter, then this would be 64 grams. And now we can finish the calculation by doing the weight, although we do want to be a little careful because it did say weight in newtons. So weight is calculated with mg, and I need to switch my grams into kilograms in order to get newtons. So this would be 0.064 kilograms, and then multiplied by 10 comes out to be 0.64 newtons. So that's how many newtons of water that would spill out. And so that's just a displacement. That's really not even Archimedes' principle or Bernoulli's principle, although we do have to remember the Archimedes' principle to make sure we realize it's sunk, to make sure that this whole volume of the copper piece makes the same volume of the water that flows out. So not as hard as an Archimedes or a Bernoulli's principle, but I think that's what this one's going to be. So here we have a block of metal that weighs 17.1 newtons, and it's submerged underwater into an underwater scale, which now reads the 15.9. This sounds a lot like the lab we did, because remember, if you were then putting something underwater, and so it's sitting on a scale, there would be an upward buoyant force, and there would be an upward reading from the scale. There would be a downward weight. And since it's balanced there, the buoyant force and the reading on the scale would equal to its weight. That's the same as saying the sum of all the forces in the vertical direction is 0. We know it's 0 because we know it always equals to ma from Newton's second law. And in this case, it's just sitting there underwater, so the acceleration is 0. But what it gives us is a way to figure out the buoyant force by saying if you take the weight of the object and you subtract the reading on the scale when it's underwater. And that's how we did the lab. So hopefully that came back to you here saying, hey, this is giving me information right here on how to get this buoyant force. This is saying if you take its weight, 17.1 newtons, and you subtract the reading on the scale when it's under the fluid, which in this case is water, the difference between those then is the buoyant force. And, I guess I don't need a calculator for this one, but 1.6 then, just check, that would make a 60, yeah. So 1.6 newtons then is actually the buoyant force. So that's really the first half of the problem and the clue of what that is giving to you. It's related back to the lab we did. This information is telling you how you can get that buoyant force. Because then it goes on to ask this question and says, well, what is the volume of the block? And we know that volume and buoyant force go together because Archimedes' principle says that the buoyant force is equal to the weight of the displaced fluid. So I'm going to take this buoyant force and set it equal to mg. That's how you calculate weight. All right, so here we go. This is buoyant force, so it is 1.6 newtons. And it's equal to the weight of the displaced fluid. All right, so I'm going to put this m with the word water underneath it to remind myself that the weight is not the weight of the object, but the buoyant force is the weight of the displaced fluid. So this is going to give me the mass of the displaced fluid. So if I bring this 10 over to here, I would get 0.16. And remember, a newton is a kilogram meter per second squared. So the meter per second squared would cancel off, and you'll be left with the kilograms. Which, if we want to change this into grams, we can. This would be about 160 grams of the water, okay. But I just want to keep reminding myself, this is the water that's been displaced. Okay, so I have displaced 160 grams of water. Which kind of makes me think about what we did in 27. Remember, the density of water is 1 gram for every cubic centimeter. So if we have displaced 160 grams of water, that must be 160 cubic centimeters that we displaced. And remember, it went underwater, it went completely underwater. And so right here, what is the volume of the block? Well, the volume of the block must be the volume of the water that spilled out, or sorry, got displaced. And so that must be the volume. And so there it is. The volume of the block would be the 160, because it would displace 160 cubic centimeters of water, which is 160 grams, which equals then the way you would calculate the buoyant force. So kind of two steps here. We got to get that buoyant force, which then tells us the mass, which then tells us the volume. All right, well, last set here, number 29 and number 30, which I'll call page 5 in my little solutions here, and say, all right, let's get to our last one on heat and energies. This is specific heats and latent heats. It says we have 88 grams of aluminum. And they give us the specific heat of aluminum. And it's warm aluminum. It's at 100 degrees. So hopefully this looks a little bit like the lab, where you took that aluminum piece and you put it in the boiling water. That's what made it 100 degrees. And then you moved it over into a cup of water. The cup of water was just water that came out of the sink. So it was about 19 degrees. And we poured just a little bit of water in there. So there was only about 48 grams of water. And then we mixed them. Now in lab, we mixed them and we measured the final temperature and used that to find the specific heat of the aluminum. So this is a lot like the lab, but in this one we are giving you the specific heat of the aluminum, and you are asked to calculate what the final temperature will come out to be. And so the key to this problem, as well as the lab, is the conservation of energy, which says the Q that comes out of the hot object, the aluminum, goes into the cold object, and maybe I shouldn't call it cold because it was tap water, but cooler water. And so there's where it goes. Now I'll put absolute values because, you know, one is positive and one is negative. Usually when energy comes out, we call that a negative, and it goes in, it's positive. And so just doing in terms of conservation of energy, it leaves one and goes to the other. Their absolute value is the same. So this would be the MC delta T, absolute value, of the hot one. So this is the metal, the aluminum. Has to equal to MC delta T of the, I don't know if I should say cold, how about the water one? And now I can put in my numbers here. So for the hot metal, this is 88, and the specific heat is 0.22, and the change in temperature would be final minus initial. And remember, we've got the absolute value, because in this case, the hot one is cooling down. So this would actually come out to be a negative number. Remember, energy comes out, so it's a negative number. But that number goes into the cold one, so that would be a positive number. And so the water was, what, 48 grams? It doesn't say in the problem that the specific heat of water is 1. Hopefully you looked that up, or better still, really, hopefully you memorized it. That's the definition of a calorie. So that one's pretty obvious, that it takes 1 calorie to warm 1 gram, 1 degree. But that's the specific heat of the water. Then we would have final temperature minus initial, 19. And technically, I guess I would put absolute values, but that one's going to be a positive. The water's going to warm up, so I don't really even need these. It's already a positive number. So I'm going to just write that as 48 times final temperature minus 19. It's this one here where the absolute value really matters. Let me just start with multiplying these together. 88 times 0.22. This is a 19.36. And if I do the absolute value of this, it would change the order. It would may go 100 minus the final temperature, so that I get a positive number here. So remember, when you subtract two numbers, A minus B or B minus A, you get the same magnitude, just one is positive and one is negative. And so this is going to come out to be negative, and if I take the absolute value, I want the positive one. So that's the same as switching the order. So that'll get rid of the absolute value signs. Maybe I'll also do this. Let's do the 48 and divide it by my last answer, so that this number here comes out to be 2 points, and I'll just go 48. And then this would be final temperature minus 19. And that helps because then I just have 100 minus final temperature when I bring that 19 over. And that kind of helps because I can do the distributive property, 2.48 times final temperature minus, and so I'll go 2.48 times the 19, so that's minus 47.12. That way, when I bring this final temperature over to here, it's 3.48 times the final temperature. And when I bring that to the other side, it's 100 plus 47.12, so it becomes 147.12. And now finally, I can finish the math by saying, take this 147.2 and divide it by 3.48, and I get a final temperature of 42.3 degrees Celsius. Yay! And so there it is. It's all about the specific heat and also the conservation of energy, with a little bit of carefulness with your math. Yeah, you got to distribute the math, and you got to watch your absolute values. Otherwise, you're going to end up with a negative number. And of course, obviously, that would drive you crazy. You would go, what? A negative number? It's not going to come out to be negative. It can't come out to be negative. One started at a, hot one, and anyway, so watch that negative sign. Easy to make a negative sign error on that one. And then finally, the last one, it looks like it's got some specific heat and some latent heat, because it says how much heat does it require, or how much heat does it take to warm up, and we got 55 grams at about negative 19. I picked that one because that's the temperature of my freezer. So when I go to my freezer and get an ice cube, it's at negative 19 degrees Celsius. And you're going to fully boil it. And so what I would call the total, maybe I'll put it on this sheet here, the total heat would be really a warming of the ice until it gets to 0 degrees. Then it would be a latent heat as I melted the ice. Then after I melt the ice, I would warm the water. And then finally, once I warm it up to 100 degrees, I have to completely break the bonds and boil away the water. And so the melting of the ice and the boiling are the latent heats of this. And the warming of the ice and the water are the specific heats. So this would be over here, would be an mc delta T. This would be an ml sub F. This would be another mc delta T. And then this would be an mlv. And so those I probably need to look up. And I probably should be careful that this first one is the warming of the ice, and the second one is the warming of what now would be water. Because as I put in my numbers, I have the 55 grams for the ice, and the specific heat of ice is 0.5 calories per gram. It's not 1 like it is for water. So earlier on we needed it for water, and that was the one that hopefully you have memorized. But for ice, you probably want to look there in the book and say, well, how much does it take to warm up 1 gram of water 1 degree? and it's a half a calorie. Now, you're only warming it up 19 degrees because when you go from negative 19, you eventually get to 0 and it begins to melt. So if I just do this first calculation, 55 times 0.5 times 19, you're going to get 522.5 calories to warm up the ice. Now, a big piece of this, although not as big as this one, but much bigger than the one we just did, would be now you got to melt the ice. And it takes a lot of energy to melt the ice. So it's the 55 grams, and it's 80 calories for each gram to be melted. So that would be 55 times 80, or 4,400 calories to melt the ice. Now once we've melted the ice, we've got to warm it up. So it is the 55 grams still. So it's still the same number of molecules. So it's still going to be the same amount of mass. But now that it's water, its specific heat is 1. And then to bring it to a boil, we have to warm it 100 degrees. We have to go from 0 degrees Celsius up to 100 degrees Celsius. So that number is a pretty good number also. 55 times 100 is 5,500 calories. And so you can see those are much bigger than this one. So really just warming up the ice is small compared to these other things we've done. And then, of course, maybe the biggest one of all right here is boiling it away. That's why it takes so long for water to boil, because the 55 grams, but the latent heat of fusion, and again, you'll have to go to chapter 13 probably to look that up, is 540 calories per gram. So this would be 55 times 540, which makes the 29,700 calories to boil it away. And by far the biggest piece of this. And so most of the energy really is added after it boils. Once you get it boiling, that's where you still have to add the most of the energy to get rid of it. And so now if we add all these together, there's the 29,700. I'll add then the 5,500. I'll add then the 4,400. And then the small one, 522.5, gives me a total of 40,122.5 calories to boil all this ice away. Warm the ice, melt the ice, warm the water, boil the water. Now, many of you may have done this in joules, so maybe I should put 4.186 joules per calorie. And let's see what that number is in joules. And so this would be 167,953 joules if you did it in units of joules compared to calories. But when you look these up, you can look them up in either calories or in joules. So either one is fine. Okay, well, again, hope it went well for you. This looks like this could have been a pretty hard one with a little bit of time pressure on you. So hopefully you were able to do well. All right, take care.